Properties of limits, part 2. Our essential question is what happens to the limit of a quotient if the limit of the denominator does not exist? So you answer that question at the end of this video. First, we should recall some previous knowledge. We remember that if you have a polynomial, say a polynomial f of x equals, for example, 2x squared plus x minus 1, we can find the limit as x approaches any value, say 3 of f of x. This will just be 2 times 3 squared plus 3 minus 1. Which is 20. Okay, the quotient rule. This will be our major rule for today. The quotient rule simply says that if you have your function f of x is some function p of x divided by another function q of x, maybe p of x is one polynomial and q of x is another polynomial, then the limit as x approaches a of f of x of the quotient is the same as the limit as x approaches a of p of x of the numerator divided by the limit as x approaches a of the denominator q of x. If this would only be used if the limit as x approaches a of the denominator q of x exists and is not equal to 0. If it is equal to 0, then we have to do some algebra before we find the limit. Okay, some examples. We want to evaluate this limit here. So this will be the same as the limit as x approaches negative 2 of the numerator, which is x cubed plus 2x squared minus 1, divided by the limit as x approaches negative 2 of 5 minus 3x. We can see that as x approaches negative 2, the limit of the denominator exists and is not equal to 0, so we can use the quotient rule. So this will be, for the numerator, we simply substitute negative 2, so it will be negative 2 cubed plus 2 times negative 2 squared plus, minus 1 divided by, we substitute negative 2 in the denominator since it's also a polynomial, 5 minus 3 times negative 2. And this will give us negative 1 divided by 11. So it's negative 1 over 11. Sometimes the denominator will the limit of the denominator will be 0. For example, here, if we substitute negative 1 in this denominator, we are going to have 1 minus 1. If we substitute 1, it will be 1 minus 1, which is 0. So, but you will see that if you draw this function, you'll see it's a straight line, and certainly the limit as x approaches 1 of that function exists, and it's somewhere here, close to 2. It's about 2. It's you can see it's somewhere, it's getting to 2. So it means that the limit of this whole function does exist. and it should be about 2. So how do we find that limit? We perform some algebra here. This will be the same as the limit as x approaches 1. The numerator is the same as x minus 1 times x plus 1 divided by x minus 1. And so the denominator cancels out with that one to give us the limit as x approaches 1 of x plus 1. And the limit as x approaches 1 of x plus 1 is just 1 plus 1, which is 2. Exactly what we found on the graph here. It approaches 2. Now I want to make a quick note. Excuse me, let me erase this first. Now I want to make a quick note. What is the difference between this function and this function, the simplified version? The simplified version of the function, as we know, is a straight line like that. This point is 1. This is x plus 1. But for this function, it is that straight line as well, but the straight line does not exist, so there is a hole at the point 1. So at 1 there is a hole. Remember, your graphing calculator cannot draw this hole, so you have to just understand the difference between the two versions of this kind of function. If the denominator does not exist when x is equal to some value, or if it's equal to 0 when x is some value. Okay, so example 2, we want to find the limit as h approaches 0 of this function. Is the same as the limit as h approaches 0, because when h is 0, the denominator is 0, so we have to simplify and cancel out something. The numerator is the same as 9 plus 6h plus h squared minus 9 divided by h, which is the same as the limit as h approaches 0 of 6h plus h squared over h, which is the same as the limit as h approaches 0 of h times 6 plus h divided by h, and the h can now cancel out denominator and numerator to give us the limit as h approaches 0 of 6 plus h, and this is now a polynomial, so we can substitute h equals 0 in the polynomial. So it gives us 6 plus 0, which is 6. Example 4. So we want to find the limit. There's a square root sign above. This is the same as the limit as t approaches 0. We can do some algebra to get the denominator not equal to 0 when t is 0. What can we do? We simply write down the same function, t squared plus 9 minus 3 divided by t squared. We can multiply the numerator and the denominator by the conjugate of the numerator. So we can multiply the numerator by t squared minus plus 9 plus 3 divided by square root of t squared plus 9 plus 3. Now you would see that this gives us a limit as t approaches 0. The numerator will just be the square root of t squared plus 9 squared plus 3 squared, which is t squared plus 9 minus 9, minus 9 divided by the denominator is t squared times square root of t squared plus 9 plus 3. That gives us the limit as t approaches 0 of t squared all over t squared times square root of t squared plus 9 plus 3. And now this can cancel out with this to give us the limit as t approaches 0 of 1 over square root of t squared plus 9 plus 3. And now if we substitute t equals 0, the denominator is not 0. The denominator will be 6. So it's 1 over 6. Okay, thank you.